As a leader in the field of tumor biology, he is the director of the Edwin L. Steele Laboratory for Tumor Biology at Massachusetts General Hospital. He received the 2013 National Medal of Science from President Barack Obama for developing new ways to manipulate tumors. His research findings are summarized in more than 600 publications, which have been cited more than 70,000 times. He is among the top 1% cited researchers in clinical medicine. Today, he is the Cook Professor of Tumor Biology at Harvard Medical School. Delegates, please give a huge hero's welcome to Dr. Rakesh Jain.
Have fun. Thank you. Good afternoon. Or good morning, almost. And then, can you guys hear me? So, my name is Rakesh Jain. I came to the United States in 1972 after doing my bachelor's degree in chemical engineering. And then I did my master's engineering degree in chemical engineering on the mathematical modeling of Delaware River. And I finished that in March of 1974 to control pollution in the Delaware River. It was a mathematical modeling computation program thesis. At that time, Indians had the reputation they're great in mathematics and science, in computer science. But when it came to experiments, they were not quite at the same caliber. So I decided to switch my thesis project, and I began to shop around. And I was very fortunate that my Ph.D. advisor, who later on became chairman of chemical engineering at MIT and then dean of School of Engineering at Princeton University, Professor James Way, he introduced me to a very distinguished tumor biologist at the National Cancer Institute in Bethesda, Maryland. Dr. Galino was a pathologist, an MD, but he thought like an engineer. He had developed a tumor in animals which had a single artery and a single vein. It's one input, one output. And I went and asked him, could I work with this model to find out if we inject a drug into an animal, how much of the drug will get into the tumor? My thinking was, for a drug to work, it has to get there. If it doesn't get there, it's not going to work. So with that simple notion, I approached him, and he said, go ahead, test this idea in my laboratory, even though you're getting a degree in Ph.D. in chemical engineering. So I was very excited about it, and what I found out, after a year and a half later, most of the drugs that are injected into patients, very little amount gets into the tumors. And that begins to explain why a lot of therapy does not work. So at that time, the thinking was, and even today in many circles, the reasons therapy does not work because the cancer cells are resistant to these drugs. I asked a separate question, a very different question. Is it possible the reasons drugs are not very effective because they don't get to cancer cells? And that became my life mission. I began to ask the question, why drugs, when they're injected into patients, do not get into the tumor in the quantities we need to reach uniformly throughout the tumor? So in my last 45 years, since 1975, I became an assistant professor at Columbia University, then Carnegie Mellon, and since 1991 at Mass General Hospital in Harvard, I've been asking the questions, why do drugs do not get into the tumor? But more importantly, what can we do to change that? Because if we can change that, we can improve cancer treatment. And what I'm going to do in the next 20 minutes is to share with you this journey, how we can improve cancer treatment by repairing, by normalizing the neighborhood of the tumor so the drugs can get in. So what's the tumor's neighborhood? The technical word for it is microenvironment. And what this slide shows you is the microenvironment of the tumor, a schematic, and let me get a pointer to show you what different components are there in this microenvironment. So either you look to your left or right slide. So a tumor, when I ask somebody what's cancer, the first thing that comes to their mind is cancer cells. But a tumor is not just cancer cells. It's not a bag of cancer cells. It's a tissue that has not only cancer cells that are shown here in gray color, but in addition to these cancer cells, the other type of cells in the tumor, and all these are nourished by blood vessels and drained by lymphatic vessels. And all these cells and these blood vessels and lymphatics sit in a matrix, not the movie matrix, but what is known as extracellular matrix, made out of collagen and hyaluron and other various proteins and other structural molecules. So when you inject a drug into a cancer patient, it first enters the blood supply, has to cross the blood vessel, cross this matrix, and then finally you get to cancer cells. So I asked the question, after I finished my Ph.D., how I can visualize the journey of cancer cells from where you're injecting into the patient all the way to when it reaches cancer cells. So to answer this question, I had to open this black box called the tumor microenvironment. And at that time, it was a black box. There was very little known about what's going on. People knew a lot about cancer cells, but they did not know about its neighborhood. There was a complete darkness. So I wrote to NIH and other agencies to fund this work, and they continued to reject me. My first six proposals were rejected. They said, this problem is not important, you're a chemical engineer, what are you doing in this area, et cetera, et cetera. So the message number is perseverance, don't give up if you have an important question. Since I did not have money, I did my initial work by using paper and pencil. I developed mathematical models. Again, I was good at it. But I said, that's not adequate. What I need to do is show actually how drugs are getting into the tumor or not. So we developed a series of animal models and technologies, and I'll show you very shortly, those are known as windows, glass windows placed in animals, and then you can visualize what's going on in the tumor in real time. But being an engineer, I was not satisfied with just answering these questions in an animal. I wanted to translate this. I wanted to take these findings from mice to patients. So I've been very fortunate in my career that I've been able to do 45 clinical trials to test the ideas generated in our laboratory. So what I'm going to do in the remainder of my talk is to share this journey, what you see through these windows, what kind of insight we obtain, and how we can take that insight and improve cancer treatment. So when you look through these windows, if you place about 100,000 cancer cells in one of these glass windows, on day 0, 5 days later, you see the tumor beginning to grow. It's getting larger and larger. Can you see that? Can you see the growth of the tumor? Okay, good. Can you see these blood vessels? The red color things are blood vessels. Now, this is if a tumor is growing in one place, and you can see its growth. This is exactly what happens in patients. What we wanted to visualize is what happens if you take the same cancer cells and put them in 3 different places in a mouse. Why? Because most cancer patients die from metastasis. That means if breast cancer will grow in the breast, it'll go to your liver, your kidney, your brain. So we wanted to look at what happens to the same cancer cells in 3 different places. So we placed glass windows on the breast of a mouse, on the brain of the mouse, which is the most deadly metastasis, brain metastasis, and finally in the skin of the mouse. And what we saw in these 3 places was blood vessels. The tumors look very different, the blood vessels look very different, but there was one thing common among all 3 sites. The blood vessels were abnormal. They were dysfunctional. And that becomes very clear when you see the next slide, which shows what you see in real time when you look through these windows. What you see in this, shown in this slide, in this movie, is the blood is flowing quite briskly in this part of the tumor, but the blood flow is not flowing here. See that? Can you see that this heterogeneity? Can you see this non-uniformity? Blood is flowing quite. Now, what is that going to do? Think about it. If you inject a drug to the patient, where is it going to go? It's going to go where the blood is flowing, right? It's not going to go where the blood is not flowing. Are you with me, guys? Yeah. So we solved this puzzle, right? Oxygen is not going to get there. Immune cells are not going to get there. You're going to hear about immunotherapy. They're not going to get there. Are you with me? Yeah. So what are you going to do now? Are you going to punt? Isn't this an important problem to figure out why the blood is not flowing? And wouldn't it be even more important to figure out how to get it working? All right, so let's do that. So there are another type of vessels which are also dysfunctional in tumor. I said to you earlier, the tumors are lymphatics. So nobody has seen lymphatics in a live animal until we did. And let me show you how. You just inject a macromolecule. This is the tail of a mouse, and you can see these are picked up. So it looks like a fish scale. It looks like chicken wire mesh, doesn't it, on the tail? But these are lymphatic capillaries. Now, if you put a tumor in the tail and do the same exercise, what do you see? This is where the tumor is. What do you see there, folks? Darkness. What does that tell you? The lymphatic vessels are not functional, right? So think about a system, a lot of water is coming in, but the drainage is clogged. What's going to happen? Pressure is going to build up, right? Well, that's exactly what goes on in the tumor. So what goes on in tumor due to impaired blood supply, dysfunctional blood supply, tumors develop hypoxia, that means low oxygen levels, low pH, that means they become acidic, and they develop high fluid pressure. And all these cause a resistance to drugs, immune therapy, you name it, radiation therapy. And they do this, these things do it by 8 different mechanisms. I'm not going to go into this is technical, but I want you to do a very simple arithmetic. Most newly developed cancer drugs cost about $10,000 a month, about $100,000 per year. Now, to solve all the problems created by these things, you'll need 8 drugs. So how much would the drug cost to overcome this problem? How much would you pay per year? Are you good in math? What? What's their number? $800,000 a year. So we said, let's think differently. Let's see if we can solve the problem in a different way, so you'll not have to give 8 drugs, but just 1 drug. And that would be, let's repair what? Let's repair the blood vessels, right? Are you with me? Because if you repair the blood vessels, what will happen? You'll bring oxygen, you'll bring drugs, the pressure will not be this high, and your therapy might work better. Are you with me? So what are the simple principle I want you to keep in mind is the following. If you're standing by Charles River, those of you from outside Boston, it's a big river. It's in Boston's famous river. And there's a Harvard Bridge on it. Now you're sitting by the bank of the river and you're watching corpses go by, one by one. One by one. And after 8 corpses go by, what do? You have 2 choices. You can take out each of those 8 corpses, look at them, why these people died, or you go upstream and find out who's throwing these people from the bridge into the water and stop that. Are you with me? So that's what we decided to do, go upstream. And let's fix the supply. Let's fix the blood supply. So to answer the question about how to fix the blood supply, what I want you to do is do a thought experiment we did many years ago. Suppose you're watering your lawn, And I'm sure some of you do that at the request of your parents in the summer. And suddenly, water stops flowing. So what's the reason behind it? The one possibility is that somebody went and turned off the water supply while you're not looking. That's a pretty simple, trivial answer, right? That would be like, if you want to stop the blood supply of the tumor, just kill the patient, right? Stop the blood flow from the heart, right? But that's not a smart answer, is it? So what else is going on? There's a kink, or somebody, like while you're not looking, your younger sibling decided to put a bike on it or step on it, right? Are you with me, guys? So if you can figure out who is doing this, how much force you're applying on then you can figure out how to get rid of this. And then you can resume the flow. So that became the next question in our laboratory. How much force is being applied by the tumor? And how can we get rid of it? Are you with me? So we decided to do a very simple experiment, and that's shown right here. Some of you did this for breakfast this morning. Take an orange, cut it like about 80%. What happened? What's happening? Nothing. This is like a modern art. It's an installation at a contemporary art museum. You sit in front of it, and you say, wow, this is pretty cool, man. And then you go to the next installation. But there's a very powerful message here. I want you to do the same exercise now with a tumor. Take a tumor from a mouse or a patient. We have done these studies on human tumors too. What do you see? The tumor begins to open up, just like this. And I'm an engineer, so when I see something opening like that, I can calculate how much force is being generated. It's contained in this tumor. And you know what the numbers are? 10, 20, 30, 40, 150 millimeters of mercury. You know what your mean arterial blood pressure is? 110. So that means tumor can squish any blood vessel it wants, if it wants to. So the question is, what is in the tumor doing this? To summarize the 20 years of work, what's doing this is the matrix. And you know what is the most deadly tumor? Have you heard about this so far from any of the lectures? Pancreatic ductal adenocarcinoma. 40 years, progress has been minimal. It's a silent disease. You don't know when it's coming. So we decided to work on this tumor because most of the drugs do not work. To do this, first we did the studies in animal models. Here's the tumor growing in a mouse. And what this image shows is blue color represents the matrix. Remember I told you matrix is what which compresses vessels? And green color shows are the blood vessels where the blood flow is quite brisk, which I showed you in the movie earlier, right? And what we discovered, and this is where the exciting part comes. What we discovered 7 years ago, that there's a drug that costs less than $1 per day. It's safe, it's generic, given to 20 million people worldwide, known as losartan. It's used to control blood pressure, can do this. What did it do? It reduced it reduced the blue color. That means it decreased the matrix. What is that going to do? Open the vessels, and that's why you see a lot of green color. What happens then? When you open that up, drugs are going to get in. What's else going to happen? The tumor is going to respond to therapy. Animals are going to live longer. So we decided to test this idea in pancreatic cancer. Now, already Dr. Rathmal described to you surgery, pancreatic surgery. He showed one of the images of that. So we decided to work with pancreatic surgeons and doctors who treat pancreatic cancer. This is the team. The best treatment for pancreatic cancer is when it's detected early. So it's localized, so surgeon can remove it. But that happens only in 10% of the patients. In 20 plus 30% of patients, tumor is detected when it's already locally advanced. That means it has not become metastasized to other places, but locally grown. It's known as locally advanced tumors. So patients who have localized tumors, 5-year survival rate is about 33%. That means 1/3 of the patients would live 5 years. But the moment it becomes locally advanced, that drops to about 10%. So only 1 out of 10 patients are going to live. So we asked the question, what if we added losartan to patients who are locally advanced, along with the standard of therapy? Can we shrink them and make them resectable so the surgeon can take them out? Are you with me, guys? Do you understand the trial? Do you really understand the trial? All right. So let me show you the results. What this trial showed is change a whole benchmark of the field. What it showed was that if you take the standard of care at Mass General or other places, only 28% of the patients become resectable from locally advanced. But the moment we add this drug, losartan, which is, as I said, less than $1 per day, you see this? This doubles. But what is even more exciting is when this resection occurs, there are no cancer. In 80–90% of the cases, there are no cancer cells behind. They're known as R0 resection. These patients live longer. So what I've done is shown you one way of improving blood supply. Let's go back to this slide and show you another way of doing that. So what do you see here? Again, the same hose, and nobody's stepping on it, and the water stops flowing. What do you think is the reason? Something in the hose? No, that's already similar to somebody stepping on it, mathematically. Turn it off, I already answered that. That will require killing the animal, right? You don't want to do that. What else? How about if somebody poked holes on it? Right? And the molecule that pokes hole in a tumor is called VEGF. And if you have a lot of VEGF in a tumor, the blood flow supply. So what I did in 2001, proposed a heretical idea that let's wipe out this agent, this anti-VEGF agent, with the drugs, and once we do that, the blood flow should resume. Now, this sounds very obvious to you, but in 2001, for 30 years, people were trying to block VEGF, not to improve the blood supply, but do the opposite. Shut down the blood supply. You know why? Because VEGF is known as vascular endothelial growth factor. That's what blood vessels need to remain alive. So when I proposed this idea, it was heretical. People were avoiding me in meetings. My papers were being rejected. My grants were being rejected. They thought Dr. Jain must be smoking something. And I was not. I assure you that. So the burden was on us. Let's show it why this is happening. So let me show you the idea. So we decided to show a movie. And this movie was made by my MD, Ph.D. student who slept next to animals and woke up every 2 hours and made this movie to show how blood vessels change every 2 hours. And what he shows was that the abnormal vessels become abnormal. So when we showed this and published this, the next set of criticism came up. That is, oh yeah, this is happening in mice. This obviously doesn't happen in patients. So we said, okay, let's test this idea. So we decided to do 45 clinical trials. I'm not going to go over all of those, but I'll show you the trial with a very deadly tumor, glioblastoma, the most deadly brain tumor, from which the late Senator Kennedy died, Senator John McCain died, Beau Biden, son of former Vice President Joe Biden. And then this tumor, the blood flow is quite impaired, what I showed you earlier. But when we gave anti-VEGF therapy, the blood perfusion came up. I will not go into details of this, but that's exactly what happened. In the patients, when the blood flow went up, they are the ones who are living longer. So this concept, what I want to leave you a message with is the normalization of blood vessels, whether you do it with anti-VEGF, other agents, or with losartan or other agents like this, can benefit not only cancer patients, but a number of patients who have diseases worldwide, more than 500 million, whose disease contain blood vessels that are impaired. And then maybe in the Q&A, I can tell you about 70 such diseases. Let me just give you 2 examples. The very first example is tuberculosis. 1.8 billion, that's about 1/3 of the world population, has tuberculosis bacteria in it. Fortunately, most of the time, it's silent. But when it comes up, the disease develops resistance. So I said, maybe we need to go back and take our lessons from solid tumor treatment and apply them to tuberculosis and see if that works. So we decided to collaborate with people who are TB experts. And what we discovered was that similar to the tumors, which I showed you earlier, right here, this same thing happens in tuberculosis. And when you inject drugs, guess what? They sit in the margin. They don't ent in. Same thing that I saw during my Ph.D. thesis in 1975 with tumors. So what would you do? You repair blood vessels. And we did. And the Gates Foundation were very kind to us. It gave us money to do this idea. After it was rejected by NIH because they thought this is a crazy idea. Guess what? Losartan and non-vascular normalization is improving delivery of these drugs 8-fold in these TB lesions. And currently that work is going on. Last example I want to give you is a pancreatic pediatric brain tumors. And the worst type, one of the worst type is medulloblastoma. This tumor arises in babies who are 3 to 5 years old. The current treatment is radiation and chemotherapy. A lot of these patients get cured. But you know what happens? 2 things happen. One, the tumor comes back invariably. It goes down the spine. It metastasizes via spine. Go down like this in babies. Think about that. Second, because of treatment, these kids lose their IQ 5 points per year. Did you hear that? 5 points per year. So I'm in a department of radiation oncology which treats many of these patients. So I've been worried about what can we do about these kids. Think about it. A peak diagnosis of 5 years, under 5 years. These are babies. And guess what? Let me, in the interest of time, just give you the bottom line. And that is, we found a drug that can do it by targeting the neighborhood, the microenvironment. And so this is what this tumor is. So the way this study is done, you grow tumors in a certain number of mice. You see it's 3 weeks after you implant cancer cells. It's confined to the brain. 6 weeks later, you see it expands. But look, in number of mice, it goes down through the spine. That's this metastasis. That's the spread of the cancer. What we found out in this study was that when we gave an antibody against PLGF, we can talk about that later on, what that is. Guess what happens? Do you see blue color here? Do you see blue color here at the bottom? So what does that tell you? This treatment is helping them and doesn't lower their IQ. It has no effect. So currently, we are testing this idea in patients, and the results look promising. So just let me end my presentation by acknowledging my clinical collaborators. I want to also acknowledge the Gates Foundation and my collaborators in TB area. I would like to collaborate my colleagues, my students in the Edwin L. Steele Laboratory. Some of them have been with me for 25 plus years. But the people I want to acknowledge are people like you, young people. I've had the very good fortune of mentoring more than 200 graduate students and postdoctoral fellows in my career who are like this at one stage, and many of them are very successful, and I'd like to acknowledge them by just giving you, would not have time to mention the names of all of them, but their work is what I described to you today. They were my partners in the journey of the last 45 years, and without their commitment, without their hard work and imagination, we would not have been able to do what I have discussed with you. But most importantly, my family, my wife, my parents, and my children, some of them are here. So thank you very much. I'd be happy to answer any questions you have. Thank you.
That was so wonderful. Thank you so much. Can we do some questions? All right. Yeah, thank you. Billy Porter, come on up. Give it up. Please sit right here.
He's from Mass General Hospital. He was there. He's okay.
Please sit.
Thank you. Thank you.
So what a fantastic talk you just gave, I have to say. and we have a bunch of questions here. So you mentioned originally that your interest was in chemical engineering. How did you go about transitioning from that into more of the medical field?
So I think, as you heard from Dr. Arasupaya, when you were in India at that time, he's a little younger than me. When you're young, you went to your parents, they say, okay, you're either going to be an engineer or a doctor. They didn't even give me the third choice of being a lawyer. So I went to my first biology class in high school, and they cut open a frog, and I couldn't handle it. I fainted. So I said to myself, I don't think I want to go in biology. So by default, I ended up being an engineer. So I came to this country to get my graduate degree in chemical engineering, which I did after master's. And as I said in my presentation, I was so fortunate, and that's something you have to keep in mind, you have to get lucky in life, that I met Dr. Galino. And my Ph.D. mentor in chemical engineering was so open-minded. He said, why not? You can work in cancer. The only requirement he had was you will have to develop a mathematical model. I said, I can handle that. That's easy. So that's what really, so when I saw the drugs were not getting in the tumor, even though others were not thinking it was an important question at that time, I said, this is it. Let's figure it out. And I know you worked in Dr. Mark Poznanski's lab. The immune therapy also fails because of the same reasons. So that's why, that was such a large question. I said, look, I'm just going to plunge into this. And I did. And it was very hard to get in. I'm not going to deny that. I was an outsider. I was not trained in biology or an MD, but I've done more clinical trials than most MDs do in their life because I have had very good collaborators. And so I think the most important thing, guys, ask right large questions. Don't ask small questions. If you ask small questions, what will happen is you spend the same amount of time which you could have spent on answering larger questions. So choosing the type of question you ask early in your career or through the circuitry which Dr. Apaya did, you have to do that. So there you go. I hope I answered your question.
Well, I too fainted from my frog dissection, so that makes me feel a lot better. And now your work has definitely impacted millions and millions of people. Could you give some concrete examples in the ways you saw that?
Sure, be happy to do that. So about 1 million Americans lose their eyes, become blind because something known as macular degeneration. Their eyes, and the eyes become leaky. The blood vessels in the eye become leaky, abnormal like I showed you in the tumor. And currently there are 3 or 4 drugs approved that were originally developed to starve these blood vessels, to kill them. But guess what? All they're doing is repairing them, normalizing them. And when they normalize the blood vessels, the eyesight is back. And this drug is given to millions of patients worldwide. So this is one example. I gave you a second example. Let me give you another example. There's another disease called schwannoma. And these patients, usually younger patients, they develop these benign lesions in the ear around the nerves. And they compress the nerves, so patients lose their hearing. And the only treatment in the US right now is radiation and surgery. Guess what? Radiation makes hearing worse. So I've been also watching this. So my colleagues and I decided to look at blood vessels of these benign lesions. And guess what? They're also abnormal. Say, aha, it's time to use normalizing agents. So we gave low-dose anti-VEGF agents. And guess what? The vessels repaired, and the hearing came back. So we did publish this paper in 2009, led by my colleague, Dr. Scott Plotkin at Mass General Hospital, who's the head of NF2 clinic, in collaboration with Dr. Emmanuel Tomaso, who was a faculty member in the Steele laboratory. Guess what? In these first 10 patients, when they received this, and 6 of them, 60% of them, hearing came back. Some of them had never heard a word. Can you imagine that if you haven't heard a word in your life and suddenly you can hear it? Especially for a young guy in a school. So guess what? Because of that, This drug was approved in the UK 5 years ago, 2014, for these patients. And right now in the United States, they're doing randomized trials. That's going on right now. And hopefully, the early results look very promising. So it should be approved in the United States also. And that's a game changer.
Now, part of what has made you so great is that pursuit of the unknown. What areas today do you think are still largely unknown in the field of medical research?
Okay. So one of the most exciting area right now in cancer is immunotherapy. I know you work on some of that. But as powerful as immunotherapy is, it helps only 15% of the patients. Do you hear that? 1-5. So there are 85% of the patients who don't benefit. Number one. Number two, 2/3 of the patients who receive these drugs, they develop toxicity. Second problem. Third problem is financial toxicity. If you go around, read the newspapers, you find out what is one of the biggest challenges Americans are facing. They cannot pay for their medicine. They cannot pay for their health care. It's more expensive here than in Europe, in Canada, and a lot of other countries. And yet, the United States is not number one in medical care. In medical research, it is number one, but in medical care, it's not ranked as the top country. That means we have to bring drugs that are inexpensive. So in my opinion, if we can bring drugs that don't cost $100,000 a year, but $1 per day, it's going to be a game changer. So those of you who are young people in the audience, think about that. You want to make a difference in 90% of the world who cannot afford $100,000 drugs. You need to think about it now and not 10, 20 years from now, when the majority of the world population cannot afford this.
So, did any of your findings particularly surprise you over your career?
Everything I have done in my career is 180 degrees of what was going on. So when I got into the area of using anti-VEGF agents, everybody was trying to starve the tumors using those drugs. I came along and said, let's use these drugs to do the opposite. Let's improve the blood supply. And I told you already, but people are not very happy about this, but now it's widely accepted. So my whole career has been discovery and findings are counterintuitive. They don't look on the surface right. But the other message is dig deeper. It's so easy to be superficial. Let's starve the tumor. Sounds good, because if you starve the tumor, you cannot grow it because you cannot get nutrient. That's what surgeons do. They take the tumor out, put it outside, don't they? They really starve the tumor, don't they? Try to do this while the tumor is inside the body. Because the drugs that will do that, chances are they will also give you cardiac arrest. They'll also shut down the blood supply of a lot of normal organs. Think about it. So this idea sounds so seductive. Let's cut off the blood supply of the tumor. Surgeons do this all the time. But can you do this in a patient without hurting supply of other organs? So the whole idea about, when I proposed the idea, the reason pancreatic cancer tumor is very hard to treat, it's because 80% of the blood vessels in pancreatic cancer are shut down. 80%. Did you hear that? So you can develop most magical drugs. How would they work if they can't get there? See my point? So then we said, okay, let's see if we can open these vessels. So in the beginning, people said, no, this is a crazy idea. You can't do this. And as I said, it took 20 years before we came up with losartan. Before that, we depleted the matrix by giving enzymes, destroy it. And that worked, but you can't give that to patients. We gave women make towards the end of pregnancy a hormone called relaxin. Guess what relaxin does? It changes the matrix of the cervix. And guess what happens? Cervix opens up, baby comes out, and this hormone goes down, relaxin, everything goes back, cervix, all right? So we tried that in mice. It worked. And we are about to do a trial in pancreatic cancer patient with relaxin. But we found out that in some other studies, not ours, that can increase metastasis. You have to stop right then and there. So went back to square one. Anyway, so to make the long story short, that's how we found out this class of drug, losartan. But what is exciting is that losartan, about 1/4 of the human tumors have tons of matrix, and these are known as desmoplastic tumors. Pancreatic cancer is the top of the list. There are about a dozen other tumors like this. Lung cancer, 25, quarter of them, same problem. Triple-negative breast cancer, one of the worst breast cancer to have, same problem, it's full of matrix. Esophageal tumor, same problem. Ovarian cancer, same problem. So you see, if you discover the underlying principle, it's like discovering E equal to mc squared. Or it's like discovering F equal to ma. You remember that from your high school? If you can discover that, you can design rocket ships, you can design cars. You understand what I'm trying to say? So what I would like you to do, instead of making a car or a rocket ship or a computer, would be nicer if you could develop the principle underlying it, so you can apply those principles to millions of things, and not just one or two things. And that has been my guiding principle. Extract the underlying truth.
Well, that was a fantastic answer, and unfortunately, it looks like our time has run out, so I want to thank you again for taking this time to talk with us.
Thank you so much, Dan.
Thank you so much.
Pleasure. Thank you.